Today we're going to be talking about retrofitting grid-tied systems with battery backup using Morningstar's TriStar MPPT 600V controller with DC transfer switch. Morningstar has been a leading supplier of solar charge controllers and inverters for over 20 years. Many of you on the line with us today have been using our controllers for off-grid applications, but today we're going to be talking about a grid-tied application. My name is Mark McHenry, and also presenting with me today is Doug Grubbs, Morningstar Applications Engineer. So we're going to be making a recorded version of this webinar available on our website, and we invite you to text any questions that you might have in the chat box on the bottom of your GoToWebinar pane. We'll address these questions at the end as time permits. So recently we announced the launch of this latest version of our new 600V controller that has a built-in DC transfer switch. I'd like to take 1 minute to highlight and review some features listed on this slide that pertain to this DC transfer switch version, as well as our previous versions of our 600V controller. Then I'll address the differences with our transfer switch version that enables it to be used in an application to retrofit existing grid-tied systems with battery backup. And regardless of the version, the TriStar MPPT 600V controller has TriStar MPPT technology, and it's very accommodating to PV systems greater than 150 VOC with long wire runs or greater radial bends from the array to the controller. If you install this controller and later on your load capacity changes and you need to increase the size of your PV array, you can add modules incrementally without incurring string sizing issues that are sometimes associated with smaller controllers. And you can see on this slide here that the controller's peak efficiency is 97.9%, which is very high for a high voltage controller. We have no fans or moving parts with this controller other than the transfer switch. It's preset for 48-volt battery systems, but it's custom programmable for other battery system voltages as well. So, for example, you could use this in a 24-volt system if you wanted to. And the advanced internal processor within this controller enables for very fast sweeping. The controller here will sweep the PV array in a fraction of a second, so it sweeps very fast, and it's able to track the true power point throughout the day. You see here that multiple 600-volt controllers may be used in parallel to manage charging from a single source input. In such parallel arrangements, the controllers will be synchronized to act as one large aggregated controller. And what this means is that all functions are synchronized among all of the controllers, including maximum power point tracking, charging, indications, data aggregation, meter and live view, battery sense, and battery temperature readings. And then lastly, you see on the slide, this controller has extensive networking and communications capabilities. And on the next slide, I'm going to show our version of this controller with the DC transfer switch and the transfer switch version of this controller that comes pre-wired and connected to a ground fault protection device. Okay, so on the left we have the version with the DC transfer switch, and on the right we have the version with DC transfer switch pre-wired and attached to a Morningstar ground fault protection device and a vertical controller on top configuration. And we've listed the SKUs for each version underneath each product. So you can use this controller by itself if you don't need a GFPD, or you can get it pre-wired with the GFPD, or you can also get the controller and our GFPD separate, should you rather pre-wire them yourself if you want to arrange the devices in a side-by-side configuration for your install, or some other configuration other than the vertical arrangement that you see here. And the nice thing about the pre-wired GFPD is that you only have to make a few connections to the controller. So you just have to connect the PV input, the battery, the grid-tied inverter, and then of course the equipment grounding conductor. So everything else is pre-wired. And the transfer switch versions of our 600 volt controller have a PV disconnect transfer switch and grid tie inverter terminals. And this installed transfer switch helps enable a battery backup solution for grid tied systems during an outage. Another phrase you'll hear that describes this application is DC coupling to retrofit battery backup in grid tied systems. And here you see the switch built into this controller is a 30 amp double pole double throw switch. It's a break before make switch, so it'll connect incoming PV power to the controller or to a grid tied inverter, but not both simultaneously. It meets all the NEC standards for switches and disconnects. And with that said, let me move forward here and describe a scenario that I think will help everyone appreciate how this controller works and how it's applied in a grid tie battery backup solution. So in this diagram that you see of a simple, efficient grid-tied PV system for a residence or light commercial establishment, we have DC power coming from the PV array to the string inverter, which then converts the power to AC power and sends needed power to your main service panel. Any excess power is sent back to the utility company for a credit, which reduces your electric bill. And this is referred to as net metering, or some people like to say running your meter backwards. But if you're a PV installer, after someone purchases a grid-tied PV system from you, you probably encounter the question, okay, so what happens when the grid goes down? And if you didn't get asked this question, you should make people aware of the answer so they won't feel misinformed and disappointed later. So let's take a look at when the grid goes down. So during an outage, what you're seeing in this schematic is the string inverter, whose operation is dependent on the grid, gets disconnected, and it doesn't deliver power to the main service panel or the utility. So this is by design and by code, since if the connection is maintained, you'd create an electrical hazard to workers who are trying to put the utility power back online. Thus, during a grid outage, even if you have a solar array, you have no power. Almost all the residential and light commercial grid-tied solar systems that have been installed throughout the world over the past 2 decades rely upon utility power to operate. So weather and infrastructure events have caused a growing number of consumers to experience the fact that their grid-tied solar system is useless during a power failure when the array is left stranded. So for this very scenario, we can apply the TriStar 600 volt controller with DC transfer switch. I'll show you how we do this on the next slide using some block diagrams and wire diagrams so you can see how this all works. In this slide, you see a grid-tied system where we've added the 600 volt controller here, which has the PV disconnect transfer switch. Also, we've added a ground fault protection device, a battery bank, a backup inverter charger with an automatic AC transfer switch, and a critical load subpanel. So in this example, when the grid is working, we're looking at the system with the controller's transfer switch in the grid on and the controller off position. So you see that right here. So the flow of power in this case looks similar to what we saw in the first schematic we saw a few slides earlier. So DC power comes from the array, actually bypasses the controller and goes to the string inverter and outflows AC power. This goes to the main service panel, and excess power goes back to the utility. You also have power going to a critical load subpanel, and this critical load subpanel, the power that goes here goes to run your critical loads, those loads that you've defined as being the most important that you need to back up during a power outage. So that might be your sump pump, your refrigerator, some of your lights, perhaps your television, cell phone chargers, and outlets for computers, for example. You also have AC power that goes to the backup inverter charger, and ultimately this gets converted to DC power that is used to trickle charge this battery bank that you see here, so that you'll have this battery bank ready and charged when you have a grid outage. So on the next slide, we're going to take a look at what happens during that grid outage. One quick note before I go to the next slide. This system can be installed so that your AC backup power to your critical loads goes on immediately when you have a grid outage. So you don't have to be in the dark waiting for the backup to go on. So with that, let's go ahead and take a look at the next slide. And so during an outage, your AC backup can be set up to provide power immediately, like I just mentioned. In order to make sure the battery stays charged, in case the outage lasts for a long period of time, you need to turn the PV disconnect transfer switch to the battery backup controller on position. So you can see here the switch is in that battery backup controller on. And with the switch in this position, the DC power flows through the controller, and it then gets regulated to the batteries, the DC power to the batteries, and ultimately that power goes to the backup inverter charger, which converts the DC power to AC power, and that gets sent to your critical load subpanel. And again, this is what allows you to have power in a outage so that you can run your critical loads, which typically are going to be your refrigerator, sump pump, lights, television, computer, and cell phone. And so during this grid outage, you have continuous emergency power from your batteries that get charged from your PV array. And then when the grid power is restored, you simply turn the controller's transfer switch to the grid on, controller off position, so then you'd flip it this way again, so the grid on is controller off. And this way you can have full power and you can sell back excess to the grid again. So now that you've seen this general overview of how this works, on the next slides, I'm going to hand off to Doug, who's going to talk a little bit more about the benefits of this DC coupled approach. So Doug, if you're ready, let me flip controls over to you.
Okay. And so we're going to look at a little bit of the benefits of the TriStar MPPT 600. It was really remarkable when we developed this product that we were able to get it in the same box, basically, as the DB, the disconnect box version. So it's basically the same as the DB box, but we were able to get a transfer switch inside there, and it made it really a decent price point, and it works great. So it's an effective way to extract energy from an existing PV system to charge batteries during an outage. As Mark was talking about, the industry has been challenged with this, how to do this for years, and this is the first time that that I know of that you can just switch over to a charge controller like this, a high voltage charge controller. For years, many people are aware of how Morningstar has a very good reputation in the off-grid market for charging batteries, keeping batteries charged, and now you can get the same quality 4-stage charging that you would get with a Morningstar controller added for battery backup. And it's a really the one thing that makes it really great is because it charges directly from the DC to DC, and it's not taking the long way around by going to AC and back into DC through an inverter charger. So it's direct charging for your PV array system. It gives you full 4-stage charging. It reduces power as needed to give you the bulk absorption and float voltages. And it could equalize. I wouldn't think most battery backup systems would need that, but it might be a little bump. You might want to give it to throw it into manually or something. If there's several days of an outage, wouldn't hurt if it's not too high. So that is also possible. It also has temperature compensated voltage regulation. That means that you get the voltage you need for the bulk and absorption and float stages. It's not having to do some kind of on-off charging, which is very common with AC coupled systems. What will happen is it's set to a high voltage level and the batteries won't be fully charged, and it will just have to shut off. And a lot of times it would take a good amount of time for the grid-tied inverter to be able to turn back on again, because that's the way when you turn on a grid-tied inverter, it takes 5 minutes generally. It's programmed for the grid-tied inverter to come on again. So this is not the best way to charge batteries. We were aware 20 years ago with our PWM controllers, so great advancement over PWM on-off switching, which was this type of turn on, connect to the array, disconnect. It's a very, very basic, not very well thought out way to charge batteries. So it's hard to get to 100% state of charge when you're having to turn it off or go at full current. So there's no way to regulate that current to the reduced levels that you need, or you have to add diversion loads often. It also requires that you handle the whole power from the existing PV system. If you have a 6 kilowatt PV system, you have to be able to handle that whole 6 kilowatts, often requiring something like an 8 kilowatt inverter charger to be able to handle that full power. Now, I'm not really just talking about inverters that are capable of reducing the current. There are these types of inverters out there, and that can be done with AC coupling, but I'm more talking about inverters that aren't able to do that, and there are existing systems that people want to get battery backup or thought about, but it just wasn't a very feasible solution in many cases because of the struggles with the on-off switching and the full power, and it's not really able to work except when the grid's on. So dealing with all that power is really a struggle. So the single DC conversion is really a big factor, and it's really going to give you the highest efficiency that you could of any type of battery backup system. So we directly charge the batteries from the PV array, and makes it a really good system. So the sizing benefits are that it's completely independent from the grid-tied inverter. So this is a really big factor because it gives you a lot more flexibility. It's really about adding more options. You know, I would say that AC coupling is a decent solution, especially for certain certain systems. Certain inverters can work well with it, DC coupling. It's not always the best. It can be very challenging, though, to make it work right, or you may have to oversize it. You don't really have a lot of choices. You have to do what you need to do to get the AC coupling to work, so which can be problematic. So what you have to do is use this really, you have to AC couple as much power as you can to get it to meet the power from the array. There's no other choices but having that full power in many cases. And then in our system, the charge controller will limit the power, and we can even set the power rating of our controller to 60 amps. We can set it for 40 amps. We can reduce the size. That means we can size the battery as we want to use it to for the loads that are needed. So there may not be that many loads that the customer wants to back up, and they want an affordable option. And so this will be could be a much more affordable option in many cases than what's available otherwise. So what you would be able to do is just use part of your array, possibly also. You could use one or two strings from a larger inverter. You could even take several inverters in some cases, and use one controller for each inverters. So there might be several inverters at a site, and there may even be a existing battery system, battery backup system, or even in some kind of UPS 48-volt system that could be set up so it would get battery charging during an outage. So there's a lot of options available as far as creating a parallel system with multiple charge controllers off of different parts of the array. And you could even, since you're independent from the grid-tied inverter, you can set up a single-phase backup with a three-phase grid-tied system. So setting up, if you've ever done three-phase backup power, it can be quite hard to manage. And for an office, you may just have a few loads. You might want to keep the business running with a few computers, so people don't have to go home if there's an outage for a few hours, or you never know how long that's going to last. And it's nice to have a single-phase backup. But then it's also good to supplement that with the solar PV from your existing system. So you can take advantage of being able to utilize that power in a very streamlined fashion. So another possibility is that you can add more charging capacity later. As I was suggesting, you could put multiple controllers into a system or add on to an existing AC coupled system. The thing about the AC coupled system, once you've reached your power level, and it's just about charging the batteries, the AC coupling is not a really great way to go. If you can meet your power loads with the AC coupling system, and you don't need more AC power, the DC power transfer switch is going to be a much more affordable option for getting like a second or third controller added to that AC coupled system. So there's I know in some places they have really big options for AC coupling, and it's not very efficient. You have to go from DC to AC, and then from AC back to DC, and that AC back to DC is really inefficient charging those batteries in that manner, and you could lose at least 10% in some cases, or at least it's not going to operate with a efficiency above 90%. So you lose a lot of power by AC coupling. There's not, unless you have AC loads at the site, It's fine for daytime loads, especially because it's a very efficient way of powering those AC loads at the site. But if you want to charge batteries, DC direct is the way to go. And this is an easy way to add that onto an existing system. So I think we covered this slide, and we can do the next one. So here's a system that would be considered oversized. So the switch is rated for 30 amps. So at 30 amps, you might be able to get a 6 kilowatt array in this example, and it's going to only operate at 60 amps. Some MPPT controllers, if you oversize like this, you'll see the battery breaker trip or something like that. So our controller can be oversized like this without tripping the battery, and it will operate. It's almost like in the morning it will operate at full power capacity. So this would be on a sunny day on the blue line with a grid-tied inverter, let's say, and in the morning it will operate at full power until it gets to the maximum charging current of 60 amps. And it's kind of sideways there because in the morning the voltage will be lower, so it's a little bit lower power. At full power, it gets to a higher power level, actually, because the batteries are at a higher voltage. So for the rest of the day, whenever it's exceeding that maximum power level, it will start power shaving. So it will only operate at its maximum current level of the inverter. A lot of times you won't need that extra power. You can charge your batteries, shown in the gray line here. The batteries have the bulk charging in the blue line across the red, and then it goes into absorption, and it's reducing power as needed to fully charge the batteries, and then the afternoon it will stay in absorption charging and maintain the batteries will be full at the end of the day. A lot of AC coupled systems, you'll have all this extra power, and at the end of the day of a sunny day, it may not even be at a full state of charge because it's been this on-off switching. And it's kind of like when if you were to drive a car and you're trying to get to your destination, you're about 80% there, and all of a sudden you just have to slam on the brakes and stop driving and just sit there for 5 minutes, and then drive as fast as you can, possibly accelerate, and then slam on the brakes and sit there for 5 minutes, and you may only make it 50 yards every time you accelerate, and you never make it to your destination. And that's the way it would be with an on-off switching scheme, unless you add with more complexity, which can add cost to the system. You would end up at the end of the day not being able to fully charge your batteries, even though you've sized this thing more than you planned in the first place. So at the bottom you see in the red, that would be a cloudy day, and the nice thing is that you get the full power on that cloudy day. So this really shows the value of having the smaller direct DC charge controller over an AC coupled on-off switching controller, and being able to use a small system if you want to. So the next slide, this shows a typical scenario where this is the same 6 kilowatt system, but in the winter here in New Jersey, you'll never see it operating at full power on the most critical months in December. So this kind of indicates that on this day, if you had an inverter, full power, or if you had an additional controller to get that full power, you would get 26.3 kilowatt hours. And then the loss would be 4.4 kilowatt hours. That's the area of the graph above that red line there. So the energy production from the TriStar MPPT controller would be 21.9 kilowatt hours. So it shows you you're getting 83% of the available power for that day, or available energy for that day, and only 17% loss on the sunniest day in December. So, you know, even though we have a parallel feature where you can add two in parallel, it really wouldn't add that much more value to just size it that big, and you can get most of the power, most of the value of your PV system with a single controller, even if it's oversized a good bit. So this is a kind of a quick graph I put together. It's not based on anything other than a off-grid standalone system that goes into absorption. You can see how the PV array gets fully charged, and before it even gets to noon, in a lot of cases, it goes into absorption, and then it keeps the loads going and float for the rest of the day, and then the next day it does the same thing pretty much. Here you can see it seems to have gone into absorption. It may not have made it into float, or may not have spent it hardly any time in float. But on this day, actually, the second day there, this is like 5 days in a row of real data from our office here in Pennsylvania. You see that if you had the full capacity, you actually don't do that much better on that day. I mean, you might get a few percent more, because actually those spikes are just cloud edge effect or something. There's not a whole lot extra power up there. You get a little bit, and there'll be days where you might need that power to get fully charged, but for the most part, that excess power isn't going to be used if this was an example of the kind of power you're using and the backup system. So if we only had that much charging capacity for this system, you would still be able to be fully charged every day, just the same pretty much as it would be right now. So this really shows the value of this solution, and for this solution you can get a lower price than you would with something like an 8 kilowatt inverter charger system that you would need to get to this amount of charging. With an AC coupling, you really have no choice but to oversize it, whereas this might be all you need, is as shown in the red line here. And that was the other thing, is that you can use whatever inverter you have. The last point here on this slide is that the string inverter and backup inverter are agnostic from the controller. So it will work with just about any string inverter. There may be exceptions, but for most part, any 600 volt string inverter, you can switch it off. It's just like a switch in front of the string inverter, and you switch it off and switch it over to the controller, and it's just charging batteries, and from the batteries you can put whatever inverter charger you want. So that's what really makes it so it gives you more options. So so you have a few more options, especially lower cost backup options and lower cost options for adding additional charging capacity to a battery backup system. So the reason it's a good deal, it'll make sense a lot of times, is that it's the lowest. It will have the lowest cost point of entry for a grid-tied retrofit for backup in many cases, maybe not all cases, but anytime you're oversizing it like that, it could be a lower cost point than having to do with a larger AC coupled system. So the charge controller can also be programmed to charge any maximum current you want. So the entry point, you can have a really small battery bank if you want. So you can create a lower maximum current and use a smaller battery bank, even than the 60 amps it's rated for. So our design avoids the conflict that you have with the grid-tied inverter, which needs to sell back to the utility. This is especially the case with these larger inverters. The bigger your inverter gets, the harder it is to do AC coupling. In a lot of cases, like with a commercial inverter, the only choice you would have is to replace part of your, replace the grid-tied inverter with maybe a smaller inverter, and or possibly take strings off the commercial-sized inverter and set up a AC coupled system separate from that inverter. So there's really not a choice in many cases. Maybe if you planned it in the beginning, but if you have an existing array, let's say you have a 50 kilowatt inverter, it's quite an undertaking to add battery backup to that. And then you have to deal with doing three-phase. You may only want to run single-phase loads. I mean, a lot of offices, most of the loads in an office are only single-phase. The lights, the computers, your refrigerator. So you can run all these loads with a single phase and not have to deal with trying to AC couple a split phase or three-phase inverter. So this really makes it a very simple solution, a very cost-effective solution. The backup system is sized to what the customer needs and not the pre-existing installation. The pre-existing installation is only going to affect you in terms of what the strings sizing limits are. So you would use the same strings, and you can do whatever you want with those strings of the array. So I think that pretty much covers this slide.
Okay, terrific. Let's move on, and let me just interject. I know we have a few questions that have come in. Just a reminder, if you do have questions at the end of this webinar, we are going to entertain them. So just text those questions in the chat box at the bottom of the GoToWebinar pane.
So this is kind of a general idea of the entry point level I was talking about. Your single controller with a battery bank sized to handle the maximum charging current from that single inverter might be a 300 amp hour battery bank, and then in addition, the added wiring might cost you, in terms of equipment costs, of maybe $8,000 altogether. More or less, this pricing is very relative to, and then it also involves maybe a 4 kilowatt inverter. So if you had a 6 kilowatt array, however, you would be paying more like what you see in the blue on the left here for a simple AC coupled system. If you want to add up the added cost of setting up diversion load control so you can fully charge your batteries during an outage, you'd be looking at more like what you see on the right side. This might also be considered the cost of a more advanced setup with an inverter that can handle and regulate the charging current. So basically, you're looking at a lower price point and getting a good deal of the value. A lot of times you'll say, oh, I'm going to get much more with this bigger system, but as we saw, you don't get a whole lot more by sizing it up to your maximum power on the maximum power day. You just don't, you know, it's not going to give you a whole lot more, and it's only going to give you the power that you might be throwing away anyway. So one other thing, one of the last things I wanted to say, but before I said that, I know we might have some people here from Australia, so I wanted to mention that our ground fault protection device is for grounded systems only. I don't think we mentioned that. And then also, if you want to use this this transfer switch with an ungrounded system, it is possible. It has a single pole battery breaker, so it is able to be modified. You can replace the single pole battery breaker with a 2-pole battery breaker for an ungrounded PV array. That means it would be compatible with an ungrounded system. We do not offer a ground fault protection device for ungrounded arrays, however. So if that is available on the market, that would be great, but we do not offer that. Our ground fault protection is for grounded PV systems only. And here's information about our string sizer. This tool is available on our website. It helps you see what kind of string sizing you can do. Here on the bottom you see the link. The main points is that you want to verify the max VOC for your lowest temperature at the site. So this is based on the cell temperature and the lowest temperature, record temperatures typically, so that you never want to exceed 600 volts for that. But I would actually say you might be concerned. It will notify you that exceeding something like 360 to 370 volts might be have issues in the coldest temperatures, that it might have to derate or turn off possibly in the early mornings or the coldest temperatures. So that's something to be consider with these systems. So some of these 600 volt PV systems have been sized up to 590 volts, and that might be something that you might not want to do with this. So you want to also ensure the total power capacity, and considering the maximum power levels and that kind of thing that we discussed. The main issue is that you do not exceed the current rating of the transfer switch, which is 30 amps. In the United States, that would mean you can't have an ISC of greater than 24 amps based on the National Electric Code. So I'll turn it back over to Mark, and I think we have a few questions.
Yes, we do. Thanks very much, Doug, and thanks for everyone joining us today. And we do have some questions that came in. Just a reminder, you see this thank you page at the bottom is our website address, morningstarcorp.com. If you haven't bookmarked it already, please do so, and you can go ahead on there and contact us if you have any questions that you need to take offline, or if you think of something later on. But let me just get to, let's just take a look at some of the questions that came in here. So one of the questions basically saying, is it a manual or automated switch when the grid goes down? So you want to go ahead and...
Oh, yes. I'm not sure we made that clear, that it is a manual switch. Some people, would prefer an automated switch. At this time, we came up with a simple solution so you can use the 600 volt controller with existing PV array. At this time, we do not have an automated switch. Hopefully, at some point in the future, we will develop that, or maybe it will be offered on the market. But this time, we do not. I can see the value of it. But one of the things I've heard people say is that, they may not want that inverter with an automated switch either, because they don't want their loads coming on in the middle of the night, and then their batteries might be drained prematurely with all their loads on, all the critical loads. They may want to turn off and start budgeting and not use their loads until they think they need it. So it depends on how critical the load's on. A lot of homeowners could probably live with this, and they may need to consider ways of getting that switch to turn on. And it's a lot more simple than starting a generator in many cases for certain types of generators, where you have to take it out and get it out and take care of that. So yeah, it just takes a minute. It's kind of like when if a breaker goes out, most people don't have a problem with going down, switching it back on. It's going to be the same thing. Your outage, oh, we're out of power. Let's go turn on our controller and let's get this solar going. So it's a simple solution. It should work for a lot of people, but of course not everybody. It's not going to be as good as an automatic switch, of course.
Okay, great. Thanks for the question. Thanks for the answer. Question came in from Jonathan. Can you have CCCV charging for lithium? What resolution do you have on the charge voltage adjustment? And I guess he's saying kind of a follow-up, could I charge to 41.88 volts, for example?
Okay. Yes. Our controllers have very precise voltage regulation control. And we actually can custom program our controllers with 36 volts, other voltages, including what you have there. It's within the range of the operating of the controller. We are actually getting ready to launch a web page dedicated to different types of batteries and how you can achieve the charging control for very many different types of batteries. And it includes information about the types of changes you can make to the parameters, to the voltage regulation. You may want to not include or change the temperature compensation limits and the temperature compensation values. You can also add special algorithms in there. So we will be presenting that soon. One of the problems with lithium is that not all lithium batteries have the same ability to use the same settings. There's no set settings for lithium batteries, and what may work for one type of lithium battery could damage another type of lithium battery. So there's also in many cases battery BMS, the battery management system of the lithium battery, that makes it can be problematic in some cases, and we will have that information on our new website, our new web page.
Okay, great. Thanks for that. And I see another question that came in. Can it be used with a positive ground system, such as SunPower? Also, would you put it before or after the existing disconnect?
Oh yeah, it's compatible with a positive. You might need to consider how it's wired. So you just have to make sure you wire the positive to the switch. So it's a double pole breaker, so that's not so wiring it that way is not a problem. The ground fault would have to be wired correctly. So actually I don't see any problem with it at all with the way it's wired as it is. So since it switches both poles, and you just would ground the positive ground, and the ground fault protection is actually compatible with grounded positive grounded systems.
Okay, good question.
And then yeah, the nice thing about having it after the disconnect is that you have a PV disconnect for the whole system, and then you can just use that single PV disconnect. you could say that you have a disconnect, considering that will switch over to the grid-tied inverter, and then you can disconnect it in a grid-tied inverter, but some inspectors may want you to put it in front of everything. So it makes a lot of sense to put it in front of the controller.
Okay, I have a question. Is this solution applicable for microinverters?
Yeah, it's not compatible with microinverters, and some types of optimizers may or may not be compatible. There are optimizers that are not compatible with inverters, so of course it wouldn't be compatible with that type of optimizer. But microinverters just have too low of a voltage, and it's AC power, so it's really designed for string inverters. So there's a lot of string inverters out there that can be used with those systems, and it's really just an option for that, to use a good charge controller with an existing PV system.
And can you use this with generators in a backup scenario?
Oh, absolutely. It's actually a really good option because you can size the battery pretty small. With a generator, you have the generator if you need it. If you happen to have several days of cloudy weather, you can just set up the generator one evening and charge it for a few hours. You don't have to hear that loud generator day after day, 24 hours a day, to keep your loads going. You're on battery backup most of the time. A lot of people that have generators can really benefit just from having a battery. That's the first step of reducing runtime for a generator. It's just charging your batteries, turn it off. Charge your batteries, turn it off. Then the next step is adding PV to that, and this is a great way to add PV and reduce your runtime, so you don't have to go out and get more fuel. You may have enough days of autonomy where you've run out of fuel or LP, propane or whatever you need. So it makes it a really good option with generators.
Okay, and I see the last question.
And another thing about the generator I wanted to mention is that the reliability of generators is, I've talked to a lot of people and they say, wow, we have had a problem with these generators. Sometimes they just stop working, and you may not have ran your generator recently, and all of a sudden there's an outage, and I bet you would have a little bit of a difficult time getting your generator fixed during an outage. So it's something that you have to maintain. It's a good low-cost option, but it could be could be problematic too. So it's nice to have a backup to a generator.
Okay, last question I see is, can this be used for applications that are not residential applications?
Yes, I mentioned that you can use it with three-phase system, with larger commercial inverters. You can split off a few strings. You can have put a combiner box with two outputs on the roof, and so you can put one or two strings. You can take even just one string, and switch it over to a transfer switch. So it can be used with a three-phase system. How you configure the inverters is up to you. You may only want a single phase, maybe two-phase. You have two-phase loads at a three-phase system, so only two of the phases need to be backed up. So you have a lot of options, and it should be a lot simpler than using AC coupled. Three-phase gets really complex, and then if you've had an AC coupled system, you can add to it really easy from just peeling off strings and then using a recombiner after the controller to have it go back into the grid-tied inverter.
Great. Well, terrific. Thanks a lot, Doug, and thanks a lot for everyone for participating and asking such good questions. I'm going to leave the screen up here just a little bit longer. Again, if you need to contact us or take any questions offline, just go to morningstarcorp.com and go to the Contact Us section and send us a message. So with that, we will be signing off, and we'll see you next time. Make it a great day. Thanks.
Thank you.